Welcome to the ARSET training, Large-Scale Applications of Machine Learning Using Remote Sensing for Building Agriculture Solutions. We're delighted that so many of you are joining us today, and wherever you are joining from, welcome. My name is McCartney, and I'm an ARSET trainer based at NASA's Goddard Space Flight Center in Greenbelt, Maryland. It's a pleasure to welcome you all to the first part of this three-part webinar series. For those that are new to ARSET trainings, the following slides provide a brief overview of the program. ARSET is an acronym which stands for the Applied Remote Sensing Training Program. ARSET is part of NASA's Earth Action Capacity Building Program. ARSET provides accessible, relevant, and cost-free training on remote sensing satellites, sensors, methods, tools, and applications. The goal of our trainings is to increase the use of earth science, remote sensing, and model data in decision-making through training for professionals in the public and private sector, environmental managers, and policymakers. On the right of the slide, you can see the different thematic areas in which we conduct trainings, and I hope you would join the listserv to learn more about upcoming trainings as they are offered. Trainings are offered online and in person and are targeted to beginners and advanced practitioners alike. Trainings are freely available and conducted either live, instructor-led, or self-guided, such as our Fundamental to Remote Sensing training. Since 2009, the program has reached over 100,000 participants from over 170 countries. All our trainings are cost-free, with materials offered in bilingual and multilingual languages, and are freely available to use and adapt for your curriculum. If you use the methods and data presented in ARSET trainings, please acknowledge the NASA Applied Remote Sensing Training Program. And if you want to learn more, please visit our website. The following slides provide an overview of the three-part webinar series on large-scale applications of machine learning using remote sensing for building agriculture solutions. So, why would somebody want to take this training? Well, timely and accurate in-season crop maps at local to regional scales is crucial for agricultural decision-making and management. Irregularly spaced time series are common with optical satellite images. Training robust models on remote sensing data often requires very large data, but processing and training is complex. The cropland data layer provided by the United States Department of Agriculture's National Agricultural Statistics Service only gives estimates of the types of crops released to the public a few months after the end of the growing season, and not their sequence or timing. By the end of this training, participants will be able to use recommended techniques to download and process remote sensing data from Sentinel-2 and the cropland data layer at large scale with cloud tools. Produce interactive plots of maps, tables, time series for investigation and verification of data and models. Filter data from both the measured and target domains to serve modeling objectives based on quality factors, land classification, area of interest overlap, and geographical location. Build training pipelines in TensorFlow to train machine learning algorithms on large-scale remote sensing and geospatial datasets for agricultural monitoring, and utilize random sampling techniques to build robustness into a predictive algorithm while avoiding information leakage across training, validation, and testing splits. The prerequisites for the three-part training are the Fundamentals of Remote Sensing, Crop Classification with Time Series Part 2, and you must sign up for and access the Databricks Community Edition. Links to these trainings and how to sign up for the Databricks Community Edition are provided. Over these 3 weeks, from March 5th to March 19th, there will be 3 1.5-hour sessions which will include presentations, demonstrations, and question and answer sessions. All materials, code, and recordings from each session will be available from the training webpage. If you are not able to attend one part, a recording will be made available within 48 hours of the training day on the ARSET website. Homework opens on March 19th and will be due on April 1st. If you will be able to access the homework from the training webpage on March 19th. A certificate of completion will be awarded to those who attend all live sessions and complete the homework assignment before the given due date. Please put your questions in the questions box and we will address them at the end of the webinar. Feel free to enter your questions as we go. We will try to get to all the questions during the question and answer session after the webinar, The remainder of the questions will be answered in the Q&A document, which will be posted to the training website prior to next week's training. It is now my pleasure to introduce the guest trainers for today's webinar, Dr. John Just and Erik Sorensen. Dr. Just is a principal data scientist at John Deere and an affiliate assistant professor at Iowa State University in the Agricultural and Biosystems Engineering Department. Mr. Sorensen is a senior data scientist at John Deere, where he utilizes large-scale remote sensing data and machine learning to unlock insights and efficiencies for agricultural producers. John and Erik, over to you.
Thanks, Sean. Yes, my name is Erik Sorensen. I'm a senior data scientist at John Deere. And I'm happy to kind of present this series to you all.
Yeah, and thank you, Sean, also. This is John, and we're happy to be part of this program. And I'm a principal data scientist at John Deere and also an affiliate faculty assistant professor at Iowa State University in the Agricultural and Engineering Department.
Great. Yep. Thanks, John. So with that, yeah, I'll take it away. So part one, we'll be dealing with data preparation of imagery and labels for large-scale machine learning modeling. Some of the part one objectives. By the end of part one, participants will be able to programmatically submit lists of boundaries to the NASS API and retrieve the cropland data layer rasters back, subsample and visualize retrieved data from the cropland data layer with interactive spatial images and other statistical plots, obtain Sentinel-2 raster files for a given area and time frame corresponding to the retrieved CDL data, and manipulate the Sentinel-2 rasters into tables in preparation for analysis and model training, as well as verify correct processing of the data via various interactive plots. For example, we'll be doing some time series of pixels and various land covers. So in section one, we'll deal with irregularly spaced time series modeling and methods and processes to deal with that. So what is irregularly spaced time series modeling? When dealing with satellite imagery, it's very common that we'll have irregularly spaced time series data, which means that we're not going to have, one image every 5 days guaranteed, for example. This is common due to multiple reasons, such as orbital geometry, variations in exact orbit timing and geolocation, and image extents, as well as atmospheric disturbances due to things like clouds and smoke or other random events that obscure the view of the Earth, which is what we care about. So, for example, this plot showcases kind of an NDVI, which is the Normalized Difference Vegetation Index, for two fields from Sentinel-2. NDVI really just showcases the levels of vegetation amounts, and so we can see kind of over the growing season for these two fields, the vegetation is low during the bare, showing bare soil before the crop grows. As the crop grows, NDVI spikes, and then as the crop gets harvested and dries out, NDVI goes back down. What we can see in this plot is that there's a lot of noise scattered on throughout these images. And these are often due to things like cloud cover that add noise and data that we don't want during our modeling process. Additionally, these two fields are spaced approximately 2 kilometers apart. However, A has about 2 times the scene coverage, and this is just caused by an orbit data overlap. And so there's multiple processes and methods that we need to consider to make this irregularly spaced time series a little bit more regular to prepare it for modeling. So what's the motivation for this example that we'll go over in this training series? So we propose a real-time prediction of the cropland data layer labels as the working example for this tutorial. The CDL algorithm is already using the same or similar satellite data sources and irregularly spacing timing to make predictions, and so this is kind of a documented example of success of using irregularly spaced time series modeling for prediction of crop type classifications. These labels are readily available via API calls, and so we can easily grab them at scale, and they're freely available. The accuracy of this is also well studied and documented, and so again, we can kind of use this process to work with the satellite image and the CDL data, and the resulting code from this training is highly transferable to other problems and use cases as well. by simply just kind of changing out maybe the CDL algorithm for a different task. And so this should be useful for these training purposes. So a little bit of background on predicting the cropland data layer in real time. So according to their FAQs, the CDL program uses medium spatial resolution, about 30-meter satellite imagery, because it's too costly to use higher resolution satellites to perform crop acreage estimation over large areas. Any higher resolution, the data scale grows really, really quickly, and so it's much more feasible to kind of train to create cropland data layer predictions at every 30 meters. The cropland data layer is also considered confidential and market sensitive during the growing season and cannot be released until after the official NASS year-end area county estimates are published in late January, early February, following the end of the typical U.S. growing season. And so the CDO only gives estimates of the types of crops, but not their sequence of timing either. So for example, if we have double crops or two crops grown within the same growing season, the CDO will say that there was a double cropping that occurs, but it won't give the order of which crop was grown first and second. So our question really is, do we really need to wait until the following year for accurate estimates for crop type? And looking at kind of this example here, we're comparing corn and soy time series of NDVI images again. It becomes really apparent quickly that from this time series imagery, we can be pretty confident in the crop type just from looking at the NDVI in this area. So for example, in early May and in June, we can quickly see that the NDVI curves diverge between corn and soy, and so we can be pretty confident in our model predictions between corn and soy predictions in this case. And then especially in late August, as the NDVI growing curves grow down, as the vegetation decreases, as the crops dry out and get harvested, we can be very, very confident about August in the crop type prediction, which is 6 months prior to when the CDL is typically released. So we can really get ahead of the curve here and make these CDL predictions ahead of time before the official model results are released for the year. The approach that we teach in this series is also very generalizable. So robust models require large-scale data management tools and approaches. Leveraging multi-core, multi-machine parallel computing is a very necessary step to scale up and working with satellite imagery. So we demonstrate these tools and approaches with this series, and so you should be able to use this same code and methods to solve any other problem as well with other data sets as well, including other satellite images. We'll use Sentinel-2 for this training series. Note that a similar approach to crop modeling with the time series imagery could be used for estimating other things as well, other than the cropland data layer labels, such as things like crop health or other time-dependent factors as well. I mentioned double cropping before. You could use this method to, for example, predict if a field was double cropped and which crops were planted and harvested in what order. So for example, we can see in this time series imagery, again, this is a clear example of double cropping. In the first part of the year, winter wheat was harvested. It was planted likely in the fall and then harvested around May timeframe. And then right after winter wheat harvest, soybeans were planted. And we can see the growing curve for the soybeans in this NDVI plot. And then additionally, the soybeans were harvested in the fall. And so we can use this exact same method to predict a double cropping by just simply changing maybe the label that we're predicting on. Furthermore, there's not many examples of statistical theory around unevenly spaced time series. And so there's not much for out-of-the-box methods to apply directly for these situations. The most common solution to applying machine learning models on irregularly spaced time series is to manipulate the data into a more regularly spaced time series and then apply more standard machine learning methods. So for example, interpolation or interval binning is often applied. The CDL algorithm actually applies the interval binning method and then trains a decision tree on it. Note that the resulting data format from this part 1 demo will support any modeling approach. So we will follow a very similar approach as the CDL does with binned intervals for parts 2 and 3 of this demo for data loaders and model training due to its simplicity. So then you can train any traditional machine learning model on this more regularly spaced time series of imagery. There are some newer machine learning sequence models, such as transformers and self-attention, that accept positional encodings of inputs and outputs and learn meaningful absolute and relative input and output information, which could facilitate direct modeling of unevenly spaced satellite data. But due to the increased complexity of those examples, we don't incorporate it in this training series. We'll stick with regularly binning the irregularly spaced time series and then training a more traditional machine learning model on that data. So that will get into section 1 of this training series, going into detail on the cropland data layer. So the cropland data layer is a model that is released by the USDA that predicts the crop types for the contiguous United States and what crops are planted in what locations. The best place to find information about this is the USDA NASS FAQs and the metadata on their site. So some relevant info and highlights. The model that they use is a decision tree classifier. It handles missing, non-continuous, non-normal, non-linear data, and it's very efficient in its computation. It also provides probabilistic output, so we can actually provide confidence bands on how confident the model is in its prediction. And we can convert that to a class, to whichever class the model is more confident in will be its ultimate prediction for that location. The input to their models, they use 3 different satellite sources, NASA Landsat 8 and 9, as well as the Indian Space Research Organization, ResourceSat 2 at List 3, as well as the European Space Agency Sentinel-2 and 2B. The imagery is downloaded daily with the objective of obtaining at least one cloud-free usable image every 2 weeks throughout the growing season. This strategy is pretty common when working with satellite imagery, a strategy of combining multiple different satellite sources as input, as it minimizes the chance of getting bad pixels or bad images due to things like cloud cover. The ground truth used for the model was the FSA Common Land Unit for crops and the National Land Cover Database for non-agricultural areas, so like cities or urban areas. The accuracy of the model is generally 85 to 95% correct for the major crop-specific land cover categories, and its resolution is 30 meters. Speaking more on the cropland data layer accuracy, as noted earlier, the cropland data layer accuracy is well studied and documented. Below is an excerpt from the USDA quality checks for Arkansas in 2022. Additional studies of accuracy can be found at the USDA NASS cropland metadata site. Some crops, for example, like sorghum, may have very low accuracy, but they also represent a tiny proportion of the farmland. So this is something important to note as we're using this to train another model. Crops that the more major crop types have more representation, and thus the cropland data layer is more accurate to predict them. So things like corn, cotton, rice, and soybeans have much higher representation in the data, and so the cropland data layer is more accurate to predict on those crop types than, say, sorghum, which have a very low representation of total farmland, and so it has a much lower accuracy. We can see here that for Arkansas in 2022, the accuracy for predicting correctly the sorghum crop type is 22%, where the other major crop types varies about 85 to 95%. And so that's important to keep in mind as, you know, if you were interested in predicting sorghum, for example, using the cropland data layer as input, you might get lower quality results than if you were trying to predict corn or cotton. So now for some context on some data, how big the data can get for these types of problems, specifically for the cropland data layer, if you're going to try to train the cropland data layer on the contiguous United States. So even though only about 20% of the United States is specifically used for cropland, any given model must run across all of the United States area to classify the land. So let's make some assumptions here. So assume that we use Sentinel-2 for land classification at 10 meters resolution, and we get one cloud-free image every 2 weeks. That's 12 bands. The Sentinel-2 provides us with 12 bands, each of them at 2 bytes, which is 16 bits per pixel. And this totals up to about 26 images total per 100 square meters. This sums up to about 7.5 million square kilometers of land to process. And this equals about 44 terabytes of data post-processed to run a predictive model. So that's not trivial. It's a very large data set, although storing this data set, about a 10 terabyte drive costs about $200 in cloud compute costs. So it's doable. But this is the primary motivation of reducing the resolution, as if we reduce the resolution from 10 meters to 30 square meters, the data set drops down from 44 terabytes to about 5 terabytes to work with. So if only using Sentinel-2, roughly about 28 terabytes of raster data must be downloaded and processed over that land, since Sentinel-2 tiles are about 110 square kilometers and have 12 bands. So this amounts to roughly 640 megabytes per scene that occur every 5 days. So that being said, this data scales up very, very quickly, which forces us to adjust our approaches to work with this data and train models on this data in ways that are efficient and effective. So section 2, we're going to be discussing Sentinel-2 optical data and some of its ramifications for using it for predicting the cropland data layer. So there are multiple things that can affect both the quality and temporal spacing of satellite data. So some example factors impacting kind of the temporal spacing. There's things like orbit path overlap, which means that as you get closer to the poles, you get more increased coverage just due to how the orbits work. The orbit path and the image capture repeatability. There's also some variance in 2 passes over the same area just based on variance in the orbit locations. And so the exact position of the images can vary east to west, which results in areas on the edges of the scenes to have more uncertainty in coverage. Thick cloud cover can also occur and obscure the view of the Earth, causing data gaps in coverage. And then also there's something called the scene classification layer, which identifies if it predicts if a image has significant cloud cover or not. Oftentimes, this algorithm has some errors and can be wrong. And so when this prediction is wrong, say it predicts that there's a cloud here when there's really not, or vice versa, this can introduce unnecessary gaps in coverage in the time series of the data. There's also factors that affect the quality of the imagery as well. So things like thin cloud haze. Clouds can kind of occur in all different shapes and sizes, including kind of a gradient system. And so sometimes it's hard to identify when the clouds are very thin, as they won't appear as kind of thick objects, but it'll just alter the reflectance values as they'll be transparent. So you can see to the Earth, you can see the Earth's surface, but it will alter kind of the reflectance values that we get back and might not be captured by something like the scene classification layer. Additionally, there's tiling system overlap. So at the edge of tiles, and the tiles is how the data is stored and queried in Sentinel-2. There's overlap in this system and slight differences between the values of the same scene and location at different tiles due to post-processing techniques of the data that Sentinel-2 provides. Geolocation and georeferencing, lastly, can also affect the quality of our data. So the location of pixels can be incorrect and vary by more than the size of a pixel, resulting in wrong information for any given point location. So here's one example of what kind of the orbit path overlap is for different locations in North America. Normally, if there's no cloud cover, we'll get a Sentinel-2 image every 5 days. However, there is overlap between adjacent orbits, which increases further from the equator. So thus, certain parts of the United States on the borders of orbits get up to 2 times coverage per satellite and results in intervals of 2 or 3 days instead of 5. And this occurs as you get closer to the equator. So the orbit path repeatability, this is one visualization, an example of that. So even within a distance of 1 kilometer shown here in the image, the same nominal orbit path has several actual orbit path variations, which can affect the availability of imagery. Each of these red lines in this image showcase one of the edges of the same orbit path, and you can see it varies quite dramatically from orbit to orbit for different dates, even across the same kind of 1 kilometer location time span. So now we'll discuss a little bit on the ramifications of the tile system, which is how Sentinel-2 kind of cuts up its images and locations and cuts up the globe into these different tile sections, which identifies how we can find where an image was taken on the globe. So some considerations to be aware of when we're processing this data using the tile system, that these scenes are captured from Sentinel-2 are processed and made available using this tile system that's a slightly modified version of this military grid reference system, the MGRS. These tiles can overlap slightly and result in values of the same scene and up to 4. There's different georeferencing or calibration for each tiles. The band values for the same scene location in different tiles can be slightly different. So what can happen is, for example, if you have 4 different images all within different tiles, a different post-processing can be applied to each of these images, which can slightly adjust the image, even though it's the same image, can slightly adjust it based on which tile it was identified to be in. And so this can cause some noise and duplication of the images in our data set that we'll have to process to deduplicate and make it so that we can actually input one image per location in the time series. Lastly, the orbit paths and the tiling grid don't line up one-to-one. So the Sentinel-2 scenes are much, much larger than tiles. The swath width of 290 kilometers versus a tile size of about 110 kilometers. The overlap at the edges of orbit paths can cover an entire tile at certain latitudes. And so this is relevant when we're talking about kind of the duplication of images and scene processing per tile. And it's just something that we have to take into account as we're processing the data for Sentinel-2. So lastly, we're going to discuss briefly the scene classification layer, or the SCL. This is another band that's provided as part of the metadata layer for Sentinel-2 imagery, and it's useful for rapid identification of data of interest. While it's not a proper land classification like the cropland data layer, it does facilitate rapid classification of per scene pixels into 12 categories. So some of the most important things that we care about is identification of cloud cover and images so that we can remove them from our time series. There is a separate cloud mask available with probabilities using the Send2 core algorithm. And we'll also use it for identifying pixels that contain vegetation in this demo. So the SCL has a 60-meter resolution using a single pixel from a single scene for prediction. However, there's something useful to note is that this SCL layer can be error prone. So there was a study done by Holstein et al., a research paper to showcase the error rates for different SCL algorithms, including FMASK, Send2 Core, and Sentinel Hub. Send2 Core is what we'll be using in this demo. So we can see there's different classification probabilities between the 3. Sentinel Hub actually performs the best for cloud classification with 99.4% accurate. Send2 Core is 97.5% accurate for predicting accurately clouds. But one thing to note here is that it also has a very high misclassification rate for other classes. So things like snow, for example, it has a very high misclassification. If there's snow on the ground, 30% of the time it will classify it as a cloud. 39.2% of the time for FMASK, it'll classify snows as clouds. So that's just something that can add noise as we're processing the data and trying to clean it up and to remove cloud cover. There can be some mispredictions using this method that can contribute and add some noise. So here's some common issues and limitations. Mentioned the geolocation georeferencing of pixels, and we're showing the default scene classification labels on the right from providers. This is an example of the SCL layer from Sentinel-2. These aren't always accurate. So for example, on the left, we're showing that there can be inconsistent geolocation of about 10 to 15 meter disagreement between subsequent images that are 5 days apart. And you can see that the images shift about 10 to 15 meters between these two images. And on our right, we have poor scene classification of an image that has thin cirrus cloud cover. This particular example The SCL can often struggle if the clouds are just thin and wispy. It's predicting here that there's, definitely farmland here, but it's predicting it as water cover or snow, or just doesn't know what it is and is misclassifying it as unclassified. And so these types of images can add significant noise as well as we're processing the image and trying to clean it up and remove clouds using the SCL band. So now into section 3, we'll talk a little bit about how to actually run this code in Databricks and provide a demo at the end. So an overview of the Databricks Community Edition. Databricks Community Edition, it provides a free environment for working within a Databricks tool. The link to instructions for sign up is listed here. You will have to sign up for an account to use Databricks Community Edition. It provides Jupyter Notebook style coding, and allows up to 10 gigabytes persistent storage on what they call their file store, where you can store generic files, tables, and code in their system. These notebooks are stored in a separate area called the workspace. Within Databricks, you can spin up small instances with 2 CPUs, 15 gigabytes of RAM, and 130 gigabytes of local storage. And these cloud compute instances have Spark enabled out of the box. And Spark is a well-known cloud computing tool that allows you to work with distributed computing on larger data sets for more efficient workflows. Anything stored in the local machine is lost when the instance shuts down. So going back to the file store, it's very important that after you're done working in your Jupyter notebooks or Databricks types notebooks, that you store any data that you would like to keep in your next session into the file store. Else anything stored on the local machine will be shut down when that instance shuts down. Another thing to note is that when you're running these notebooks, and any code that takes longer than 60 minutes to run will cause the node to shut down automatically and will time out. However, as long as you're interacting with the notebook, writing and running code manually, it will reset that timer and the instance will stay up longer. So for example, if you have a script that takes longer than 1 hour to run, it's recommended to go into maybe like another notebook and execute any command to reset that timer countdown, so you have another 60 minutes to run any jobs that you're doing. So we do provide some code and materials for this demo. We'll provide 3 data processing scripts for part 1, including CDL acquisition, Sentinel-2 acquisition, and final data manipulation. The code we created it in such a way that it is generalizable to new and other problems. So the CDL table could be any ground truth label and point location and time frame. And the rest of the data acquisition and modeling, including the processing of the Sentinel-2 imagery, can remain the same. So for example, if you had labels on crop health or vegetative stage or any other types of land cover classes, you could replace the CDL processing with that to change the problem structure. Any systematic error from the CDL will also likely pass the models trained on it. We mentioned this before. So for example, if you were really interested in training sorghum, just know that the CDL has a higher error rate for predicting sorghum. And that error will pass on to any models trained on these labels. To get data as it would exist after running the scripts in this training demonstration, you can download the zip files located with other training materials for this course. And if you want to download any of your files from Databricks to your local system, you can do so by going to the URL and changing this path to the directory path to where your file exists in the file store, and then that will download the file from the Databricks system onto your local machine. So high-level overview, the code steps we'll be taking for processing and storing this data. Step 1, we'll define areas of interest, or AOIs. Step 2, we'll require the corresponding CDL data for those AOIs. Step 3, we'll search and filter for available satellite data. Step 4, we'll acquire the corresponding satellite data. And then in step 5, we'll rearrange into a Parquet file of a satellite band value data into a single row per pixel location and season, with columns for time series components in the form of lists of values. So for example, all the band values and scene dates will be in a list format saved as a Parquet file. And this is to support kind of the modeling processes that will and the pipelines that we'll develop in part 2 and part 3. It should note that Parquet file is a well-known file format system for efficiently storing larger data sets that has more support than, say, something like a CSV, which has very low efficiency for storing very large amounts of data. In this demo, we'll also be working with a couple of APIs. So in place of manually retrieving data, APIs make data acquisition and processing significantly more scalable by providing a consistent interface to search for and retrieve large amounts of data via web requests. And so we'll rely on two APIs in this demo for data acquisition. The first API is the CDL API from NASS data to get the CDL labels. And then we'll also use the AWS Stack API for Sentinel-2 imagery searches. The Sentinel-2 image raster data can be downloaded via a web URL, download links, that we can access directly once known from the imagery search that we'll conduct. So since these are large, they will slow down processing. So we'll do our best to minimize the downloading of any superfluous or low impact scenes, as this is the bulk of the data processing that we'll do in this course. So the first step, I mentioned we have to create an area of interest or an AOI for the areas that we're interested in training the model on. So the only prior step is defining these AOIs. We use the NASS Geodata Web GUI to draw 7 boxes of area of interest that we're interested in, and then exported them as Esri shape files. Then we convert them into bounding boxes using the left, bottom, right, and top latitude and longitude coordinates, and then convert it into the EPSG 5070 coordinate reference system. And this is just a requirement by the NASS Geodata API. We provide these bounds already in the CDL acquisition code, so you won't have to necessarily reprocess this for this course. But if you wanted to get different area of interests, you could follow the same process to get these bounds. So here's some example Python code to get the bounds from the zipped Esri shape files from NASS Geo that we get from the web GUI. Ultimately, what it boils down to is we'll get the list of the file paths for the downloaded shapefile boundaries, which are zip files. We'll read those shapefiles into a GeoPandas data frame and then append those data frames to a list, so that we end up with a list of data frames that contain the shapefile information from the zipped shapefiles. And then we'll concatenate all of those data frames into one single large GeoPandas data frame that contains all the boundaries of the area of interest that we're interested in, and convert them into the coordinate reference system as specified as necessary by the NASS Geo API to prepare for the acquisition of the cropland data layer data for those AOIs. So now we'll get into the CDO acquisition code and just a summary. The results of the first part are spatially downsampled version of the CDL for the user-specified AOIs that we just generated. This code part executes pretty rapidly in only a few minutes and results in a Parquet table with a single 30-meter square pixel a year per row with associated CDL estimate. So for each year that we're interested in, and for each of the AOIs, we'll get the cropland data layer predictions from this API. This is a kind of a summary table of the data that we get in part 1 from the CDL API. We can see the top 5 CDL categories across all of our areas of interest that we pull, and as well as the percentage of entire data set per year that each CDL category represents. So for example, in 2021, the soybeans represented approximately 36.6% of the land cover for that year. And we can see stats for the other crop types for these area of interest and years in this table as well. So now that we have the CDL labels, we can acquire the Sentinel-2 imagery that we'll use for training to predict the cropland data layer label. So for each of these pixel years from the satellite, from the cropland data layer acquisition code, we will acquire the associated Sentinel-2 data for that entire year and saves the data into a Parquet table. This part is the bulk of the data processing that will be performed for the series, and it takes quite a long time to execute. By a long time, we mean longer than an hour. So note that if you let this running, it will time out the free version of Databricks. And so to reset that timer, you can run manually some code in another notebook just to reset that timer so that this can process in the Databricks Community Edition without timing out. Note that due to the previously discussed tile overlap and post-processing techniques that Sentinel-2 does to the imagery, there will be duplicate images for the same tile. And there's an example of this where there's 2 rows, each containing 1 pixel worth of imagery for aligned with the cropland data layer label, taken on the same date in the same tile. It's 2 images with slightly different values. And so we do need to do a strategy to deduplicate the images to reduce the noise in the time series and make a better modeling, make a better data set, clean up the duplications before we train for modeling. The results here results in 123 rows total available for this particular pixel and year. Each row includes the band values for that location from a single scene and date. So the band values, there's 12 band values for Sentinel-2, including kind of blue, green, red edge, etc. This contains all of the pixel values that we could pull from the Sentinel-2 and available from the Sentinel-2 satellite, as well as the associated label. And so we can use this to design our data loader to prepare to use these band values and structure it in a time series format to then finally predict the cropland data layer prediction for this location and year. So we can plot the results of the Sentinel-2 acquisition code here using the same NDVI signature across a growing season. Given this plot, we can clearly see that there are errors in the scene classification layer that we discussed before. So for example, there's clearly an error in classification where it's predicting a topographical casted shadow, which we know in this area, this is just farm fields and there's no topographic things that would cause casted shadows. So this is likely caused by other things such as like cloud shadows or other errors in the system. We can also see the issue of the duplicate data showing up in this time series where these 2 values are very close together on the same image or the same date. And so we need to handle the duplication of values, deduplicate it before we plug this data into a model training system. And then lastly, again, there's error in classification in the scene classification layer where it's predicting not vegetated areas, where this area is very clearly vegetated using the NDVI values. We can clearly see this is vegetated date. And so just to note again, that there are errors in the SCL that can cause noise even after processing the data that we will have to further clean up before we enter the model training phase. And so lastly, the last step we do to the data after we acquired the cropland data layer and the Sentinel-2 images and the pixels per cropland data layer label, we will finally combine all available scenes into a single row for each pixel year. So instead of having one row being 1 pixel for one location, we will concatenate all of the time series of images into a list of values from the scenes for each row, including the band, tile, image dates, and SCL value, concatenating them all into one row. And then these list of values are then converted into binary strings for more efficient storage, eliminating the list data type and commas for everything except for the tiles column. So we do this so it's more efficiently being stored, and this also makes it easier to read in this file, this data format when we're working with TensorFlow datasets in part 2. So the results of this grouping, it means for each pixel with 123 scenes, we would have 123 by 12 values in the list in the bands column. So 123 dates. Each date has 12 pixel values associated with it. And so this will be stored kind of in this bands in bytes format and then stored into Parquet format, ready to be ingested into a TensorFlow dataset, which we'll do in part 2. So with that, I'll hand over the presentation to John, who will give a demo of the code, and that can be run in Databricks.
Thank you, Eric. So as I jump into the tutorial or the demo part, I'd like to first start out just quickly going to the place where we drew boundaries for this demo to show people what it looks like. The links were in the slide. Here you can come to Cropscape, and within Cropscape, you have the option to use some of their tools to draw boundaries. Certainly this isn't the only way, but it was a fast way to do this, especially because our data source is coming from the CDL. And you can look at the CDL overlaid on the map when you're drawing the boundaries. So we actually focused on the lower Mississippi Delta for this tutorial because of crop diversity. So I'm just zooming in here, but it will refine the resolution as you zoom in. And again, you can go in, you can zoom in as much as you want and draw your boundaries. And then once you have them drawn, there's the options to export them. So you can see export area of interest after drawing your boundary. And this is all we did. So then you can use the code also to extract them. And just note it's in EPSG 5070. It's not 4326, which is not, in other words, it's not latitude, longitude. So, all right, let's move on to Databricks. So in Databricks, we have the main page you will see when you first get into it. Here, it's giving you options to import data, create a notebook. They also have a guide, like a tutorial. It's really not a bad idea if you want to go through this really quick to look at this in case you forget what we discussed or you have questions, because we do not do a comprehensive discussion around Databricks itself. We are just trying to show how to use the tool to do what we're intending to do. But there's more functionality within here than what obviously we are using. So it's a great tool, and we encourage you to explore that. If you are to create a notebook, it's going to look just like a Jupyter notebook. So, and I'm going to jump in some of the ones we created here. And then also, we typically don't upload data via this. We'll go into catalog and then DBFS, which is the DBFS is Databricks file system or file storage. And so this is the persistent storage. It's not on a temporary cluster. Also note that if you want to get any work done, you're going to need to start up a cluster. That, again, in the quick start guide, they'll teach you that. But here you can see if you come to right here, compute, it will take you to this particular page. It should look something like this. And within this, you can create a compute. And so if I were to do this, it will give me the option to enter a computer name. There's not really much other options you can specify here with the community edition. So you don't need to worry about configuration too much. If you have an actual subscription to Databricks, there are many options here. So, all right, with that, we'll jump into part one. I'm actually going to take you through three parts and then a final data quality check, so to speak, on some of our process data. And we'll probably spend most of the time in part one where we acquire the CDL data. I have a lot of code there to visualize it. And then part two, we'll spend a little bit less time, part three even less time, and then we'll finalize some of the this discussion with plots in our quality check scripts. So, all right, with that, we'll jump into the first one. I have some notes in here. I try to put comments so that you can see what each part of the code is doing, and we also provide some links where relevant so you can go and look for yourself at some of our sources. But this really starts out, most notebooks are going to start out with some type of pip install. We're working in Python. And then we'll jump into imports. You'll see the imports for the notebook. I try not to, or we generally try not to import things down further into the notebooks. We try to do all the imports up top so you see what's needed. Just note that you want to run this first, because if you don't run this and then you come back and try to run it, it will kind of restart your notebook. You'll lose it kind of flushes your memory out, so you would lose anything that you loaded. With that, we'll have some helper functions here. Most of these are going to be around geospatial functions and web requests, and a couple other things that are useful from PySpark. So, because that's the main reason why we're using Databricks here, is it supports PySpark and it works really well for querying and working with large data tables. So I have a few helper functions I first specify. These helper functions are needed for, some of them are needed for visualization, some of them are needed for actually getting the data, so they're actually querying APIs. This particular one, I'll just walk you through this. I tried to put notes here, but things like this, which match the color scheme for the CDL, allow us to make some nice plots later on. And so again, you can kind of see how we are getting these things. We use, as much as possible, we use functions that can just grab data off the web. So this particular file comes from NASS Geo. And then as we go down here, we're going to see some helper functions again. That this is primarily getting the doing the majority of the work to get it's doing the query to the API, the NASS Geo API for CDL data. So when we send a query to it, it has certain requirements or needs to see a bounding box and for instance, a year. Because between those two things, you can get CDL data. CDL data is a once per year thing. So we have some defaults that we put in here. So if you just call this, you'll get back that data in a certain format. Of course, we try to put notes. It comes back as a bunch of bytes, and it's really a TIFF file, but it's a bunch of bytes. So you need to do some conversions there to actually see it as an image, and we'll show how to do that later in this file, or in this notebook. Again, these are some helper functions. It may not be clear what these are doing, but it allows some manipulation to the data for plotting and sampling. And again, we try to put some notes. This is the helper functions section of the code. As we come down here, again, we try to title these appropriately. Some functions to plot the data and get statistics. Again, this is useful for quality checking, making sure, especially if you're trying to train models, you want to make sure that you have a fairly evenly sampled data set. It's not too skewed towards one class. This is something you're going to want to check as you sample your data. Then again, some plotting functions. Actually, within Databricks has some very nice plotting functions. And they actually, I believe, use Plotly, which is an interactive tool. It's a very nice tool in the background for some of their work. But for spatial plots and some complex image plots, they don't really have as many tools directly. So we do create a few different functions in here to help plot some of the images. And then this is finally a function to help read the bytes of an image. So if you have questions on this, you can put them in the chat. But this is something that we really feel that it's better to try it out and play around with it, and maybe get a feel for what it's doing. So, all right. So moving on down. And I try to put notes that this was primarily if something was primarily for debugging or getting info. So here we get into the visualizing of the AOI. So we've drawn these boundaries. We actually define them here. I've copied and pasted some of these boundaries in a certain format. These are just the min, max, lat, lons. And then we're gonna use those along with, so these are for this BBox list, and the years are for training data. This is for the test data. We come down here, and I actually call some functions very quickly to view the data to see what's in there. So in this case, I just use the first boundary, and I use the year 2018, and I get some CDL data back. And what we do is we look at some box plots and some an actual map of that. And these are all interactive. So the functions that the helper functions defined above allow you to create an interactive map similar to what you would see on the CROS website, where you have the interactive cropland data layer available. So again, this is all Plotly in the back end, but we can see some statistics about what types of crops are in there. In this case, I'm ignoring anything less than 1% to clean this up. And we can see there's quite a diversity here with soybeans, rice, corn, and other things. As we move on down, again, we kind of look at, in this case, what I'm calling the test data set, where it's a very dense area of various crops. We're getting this for 1 year, 2019. And again, I want to look at the diversity or the distribution of crops here, so that when we do test the final model, we know that we're testing it across a broad range of different classes. Okay. As we move on from there, what we want to do is we're actually going to end up subsampling a lot of our data, because these boundaries that we create, we want to draw large boundaries to get sampling over a large area. But if we were to actually densely sample that and acquire Sentinel-2 data for it, it would be too much data to work with on Databricks community. So and really for most people on their laptops for a demo. So we wanted to make that a little bit more lightweight, even though it will scale. The methods here will scale to very large data. So in this case, I have a function to sample the raster, and we have an interval that you can specify how much you sample it by. So this will generally space it out evenly, both in the horizontal and vertical directions. So this is just a default interval of 3, and this is pixels. And then again, some supporting functions for that subsampling is provided right here. So here I actually show a plot of what that looks like to subsample. And the intention here is this may look kind of interesting in terms of how these lines, these black lines are here. But what this plot is intending to do is show you how it's been subsampled. So if I were to zoom in, and it's important to view your data to make sure whatever your code is you think it's doing, that it's doing it the way you intend. If I zoom in here, what we see is that indeed, if I've specified an interval of 3, I see that actually happening. So what I've done here is I've basically blacked out all the pixels that didn't get sampled, and the ones that did get sampled are given their original CDL value. So if I zoom in even further, it can be seen very clearly that subsampling of 3 pixels was effective at doing what we intended to do. So here we have 1 sampled and then 2 ignored, and that's in both the horizontal and vertical direction. And then, of course, we can reset the axes on this with this. So the nice part about these interactive plots is we can kind of zoom in and check things like that. I also zoom in on this in a different way. I wanted to look essentially at the extents of the original data, making sure we were, again, subsampling correctly over the entire interval. And here's again an example of that. It's just another way to view the above, but it was instead focusing on latitude and longitude instead of just the image plot, which is why you see it like that. So again, this is maybe not so clear what was happening, but we were trying to view the AOI, the boundary that we drew in latitude, longitude, and kind of looking at the subsampling over that. So that's why it's kind of warped like this. It's not. It's in latitude and longitude. All right. Now, we've verified that our functions work, and now we want to actually, scale this. So here, I just simply use the function defined above that we know works to retrieve data over our boundaries and years. This is for the training and test data. So we get the data. This is now a list of bytes. Now we're going to then quickly come down here. We don't use this, even though this function is available to analyze some of the statistics. We don't use that, but here we can come down and actually plot again one area, just the first boundary, first year. And what we're doing here is we're actually taking this and eventually subsampling to an interval of 10. So this doesn't have the spacing between. It just shows, again, double checking that as we expand out our subsampling, it's still doing what we intend. And it did. It very coarsely sampled one of these areas. So from there, we actually end up scaling this even more to write this out. So in this case, again, we can see the interval is set to 10, but what we're going to do here is we're going to, well, the default interval is set to 10, but we're going to essentially run this over all our data now. So we've actually got the full rasters available, the full byte strings of the data, but now we need to subsample it and then write it out to tables. And so that's what we do here. Now we do it with the test data set first. That one, we densely sample it because it's a very small area, and we want to have some nice plots at the end. And so we sample that, then we write the results of that after we sample it, via this function, and then we read it back in and make sure that this is just a check to make sure that it wrote properly. So we see about 15,000 rows, and so that seems very reasonable. Same thing here, except now we are going to loop through all the training data, and we move to a sample interval of 15 to be very coarse, because again, we want to limit the data significantly over a very large area. So we have 7 different boundaries. We tried to give a very large area, and in turn, to limit the data, we have to subsample. And then finally, again, we read the data that was written out back in, and we do a couple pivots on the table to see that the data looks all right. And that's where we're looking at right now, again, a table based on some different years and the crop type and the percentages that were available for those different classes. And if you'd like, the nice part about Databricks, I'll show this later, is that you can actually add a visualization if you'd like. And so if you wanted to see a bar plot of some variable or a histogram of something, you could do that. So as an example, if I were to drop in a particular column, it would then try to make a plot of that. In this case, that it's not doing anything, but you would be able to decide how, if you play around with this, you'll get a preview of how it would look if you tried it. So just know that's a nice feature in Databricks that you can utilize. All right, and then so as we move down, again, some more advanced pivoting or window functions to view the data, and that concludes this script. So at the end, we just kind of verify that it processed correctly. All right, so now that data will exist, and that data will exist within our DBFS system, as I mentioned before. The way I've set it up is to write out to one of these files. So we'd have the dense test, as I mentioned, and then the subsampled CDL for training and validation of models. And so you will be able to see something similar to this if you're in the Databricks file store. After you run our code, it only takes a few minutes to run. It's a very quick running code. And if you were to dive into it, you'll see that actually a Parquet file is not a file, but a set of folders based on partitions. And then you finally have some files way back here that are what are the actual Parquet files, and these are .parquet. So all right, so that's part one. Now we have our CDL data, but we need to get satellite imagery associated with that. So we move to the acquisition code for that. This is increasing complexity. There's also a lot of places when you're acquiring Sentinel-2 data to possibly make a mistake, especially when doing it at scale. So this code took a lot of time to write. It's just a note that you may not understand everything that's in this code right away because it's quite complex, and there's subtleties to it that are important to just know that if you change something, it could impact your data quality. There's subtle things that have taken a while to work out, and so we provide this to you as is, and just note that it is on you to double check that it's doing what you expect it to do. We believe we worked out most of the bugs, but yeah, we want to make sure as a disclaimer, you know that, hey, always double check your data after processing to make sure it's what you think it is. So as mentioned, When we start this code, we're going to install different packages and then import the what we need here to do the processing. Again, mostly spatial libraries. We're not doing a lot of plotting in this particular file. This is just mainly for processing. And one thing that I'm going to highlight here is we do multi-processing. We don't use PySpark to do the processing because I found it to be quite unstable for the goal of when you want to actually parallel process with very unique functions, and that's what we do here. So here we just rely on Python standard processing functions. So as we go down here, we do have a couple helper functions that, like we did in the last file. This one particularly deals with the fact that, again, NASS geo data that we got, it likes to, the API, it dealt with 5070. Our bounds, therefore, are in EPS G5070, and we want to convert those bounds to 4326 when we're doing searches. We still use the bounds that we originally defined when we're doing the imagery searches instead of the points, because just it's a quick way to easily do our kind of searches for scenes. Maybe a better way to do this that someone could come up with is, and it wouldn't be too hard to do, is to take the Sentinel-2 tiling system and group all your data ahead of time from the CDL into tiles, and then do the processing. But here we don't do that. We just use the bounds we originally defined to do our imagery searches. Okay, so here's the actual query function we use. This is how we get Sentinel-2 data back. Well, in the sense of when we're looking for what's out there. So we want to know what's available, and we use this stack API that's essentially at this location right here. It's provided via AWS. It's open to everyone, so you don't have to have an AWS account, and that's the advantage of Sentinel-2 data here is the availability of it. These are cloud optimized geotiffs that essentially are made available. So this returns the available cloud optimized geotiffs, and it also gives you links to those files. So we end up being able to just download them via web request, which is a very nice feature, and it scales very nicely. So it's open to all, and it works really well at scale. All right. As mentioned, we do kind of chunk the data in this case by bounding boxes in years. It just makes it more manageable when we're doing our imagery searches. So we're going to have some target time frame when we do an imagery search, and some target area when we do a scene, imagery or scene search. And so the way we've chunked this is again by the bounding boxes and by the years, and we've just defined the time frame as being from the 1st of January to December 31st of a given year. So if the year is 2019, we search for the entire year for the available scenes from Sentinel-2, and those are what we're going to process. So there's some helper functions here to split that data apart. It's first getting the data from the CDL paths that we just mentioned, the ones in the Databricks file store, and then we're going to split that up and decide how to for loop it. All right, moving down. This is an asset list of what we're going to get from what we're actually going to download and process for files. I got this. These names are important to keep as they are. They are the same strings used by the Stack API to denote their assets. And then here I put a reference. We are not going to process we're not going to get data from any pixels that have they're missing data, or there's a saturated pixel, it's unclassified, there's high cloud cover or high probability of cloud cover, or if there's snow or ice. We ignore all of those, but the rest of these we are going to allow data to come through for. All right, so one note here, we made this code efficient so that, again, as noted by Erik, these clusters will only stay up for a certain amount of time. After 60 minutes of running a particular cell, the cluster will shut off. I do have a cluster on right now. You can see it's green. you know, that may shut off earlier if I'm not using anything than an hour. But if you just strictly are for looping or processing one cell, it will shut off after an hour. So because of that, if we want to restart this, we want to get all our existing data and not reprocess that. We want to actually start from where we ended. So this function allows us to do that. And so that's there. And then, you know, a little bit, we want to monitor that we're not getting too much data. So I have a function to check the data size. Again, this is really focused on I can actually run this right now to see what size the dense data is, but this was focused on the dense data set. So it's only 0.2 gigabytes, not too much data right now from the actual CDL data. This is after having processed the Sentinel-2 data. So this is showing what exists in the file right now because I've already run this code. And just note that if you were to run this code for I have two different file paths here. If you run it for the train test data, you will never be able to finish it. I mean, it would take days and days of rerunning your script because there's so much data. But for the test data set, because it's small, and that's the one I have specified, you should in 1 or 2 runs be able to complete the processing of that data within this script. So it should be able to acquire all the Sentinel-2 data available for that particular boundary. All right. As I come down here, we have some deduplication of scene IDs. Again, it's something to primarily eliminate what we believe to be reprocessed scenes. So we want to eliminate the original one and get the most up-to-date one. And then finally, we get to the real meat, the real engine of this, and that's the loop to retrieve and sample the Sentinel-2 data. I won't go into a ton of detail on this because it's quite complicated. Suffice to note, it does rely heavily on raster I/O, and it is using multiprocessing to try and move as fast as possible. There's only 2 cores on this particular Databricks instance. If you have a larger machine, because we aren't really relying on Spark here, you should be able to easily, you know, take this code and just change a few file path pointers, and you know, be able to run this on your local machine. And that's the way we intended it. This part that would really be the most important part to scaling, and where we don't use Databricks or we don't use PySpark at least, can be run on other resources. So we have one function to sample the geotiffs, and then we have this other function that kind of more generally speaking is helping eliminate, as I mentioned, certain bands, or certain, I shouldn't say bands, but certain classes within the scene classification layer, like dense clouds. It's not even, it's for scenes that don't have a lot of valid area, it's not even bothering with them. So it does a lot of the work here to, again, just make sure we have a clean data set in the end, sample it as fast as possible so that we have a highly scalable data processing pipeline, and then eventually it writes it out into the Parquet files. So, and then this ultimately, it writes them out into certain partitions so that in the end you have one kind of big Parquet file, and you can query that, and I'll show how to do that in the last step. But this is really intended to scale, and it works very well. So yeah, once you run it, you will see some output below. If you do see errors like this, don't worry too much about it. Generally, you'll see it something along the lines of it's starting a worker, and then it'll tell you the scene that it's processing, the idea of the scene. It'll tell when it started, and it'll tell you when it finished. So you can kind of track progress as time goes on. In this particular case, you know, I actually reran this and started where it left off, and it finished up real quickly. So this is the kind of output you see. So, all right. With that, after you're done with that, you will have in your data store or your Databricks file store, you will be able to see something like this, where we have what I'd call an S2 sample. That's how I've labeled it. And then under here, there's a few different files. We'll have the S2 sample. This is the training and test data, which again is so big that you're probably not going to be able to run it here. but we will, in part 2, we will upload a zip file with all of that. We'll make that available to everyone. We'll upload the zip file and just unzip it so it's all available. But the dense one you could probably finish. And if I were to drill into this, again, we'll see that there's a partition on the bounding box, and then there's a partition on the year, and then there's a partition on the tiles. And then we get to, from there, we see here that there's a bunch of scenes available in each of these tiles. In this particular case, it was 2 different reprocessings of the same tile, but there shouldn't be much overlap in dates between these 2. So like as an example, we wouldn't expect, because 11/12 was one of the reprocessed dates, we won't see that available here. So it's deduplicated that. Okay. All right, moving on to part 3. And this is the final step in the processing. The intention of this is really not to, we don't get any more data at this point. We just manipulate it so that it's friendly for modeling. So we're moving it into more of a time series format. As we mentioned, we're dealing with a regularly spaced time series. So because of that, there's an uncertain amount of available imagery for each pixel location that we have from the CDL each year. And so we need something that's very flexible according to that. And most of the time, that's something like a list. So we do utilize list to a point, but we actually end up converting to byte strings ultimately. And that ends up being the format that we use. So if I scroll down here, this particular part that's commented out will become useful in part 2 when we actually extract the train and test data. And well, if we want to do that, we need to unzip it. And so we'll provide zip files, but we also provide code to unzip files. So that's commented out, but it's available here. And then we have, as typical, the import functions, and then moving right into this. I mean, really, we jump right into the meat of this code. This is a very complicated piece of code. Again, it's really not something you should touch until you're really comfortable with it. But there's certain parts that you could probably add some things in once you understand it. But it does quite a bit, and it's using functions that are not what are typically seen in Python. They're PySpark specific things like create, map, array. And so we're ultimately, I'll walk you through what we're doing, but what this code does is it first pulls all the bands for any given pixel location. Well, for any given row, it pulls all the bands from that row into a single column array. So each row currently, from step 2, each row is just a single pixel on a single date where we sampled a scene. And so we'll have 12 band values. We'll have a scene classification value for that. We'll have also some type of CDL label and an image date, things like this. So what we do is we got to pull all those band values together. We got to group them together into a single list or array. So that's for one date. After that, we also create a dictionary. So we have an image date and then the array of band values, bands 1 through 12. And a scene classification layer available for that. So that's what that's doing. It's just create a dictionary. So that's step 2. Step 3, now we need to start moving towards some type of time series format, because we only right now have it as a single date. We need to have each row contain multiple dates. And therefore, essentially, we have a lot of data. If we're talking about an entire year, oftentimes that could mean 40, 50 different actual scenes that were sampled from, depending on what was blocking it or where it was located. If there was overlap with another satellite pass, but we need to group that all into one single row. And so the bands are all grouped into one column. So it's essentially a list of lists. So each, as mentioned, we're going to eventually end up with something that each sublist is 12 bands, and then the entire list is, the different scenes. And so then we'll have image dates associated with each of those sublists, tiles, etc. we also make sure to sort those in ascending order so that it's a time series. Otherwise, if we don't have that order, what we're intending to do with time series modeling would be more difficult. So, and essentially we don't get to take advantage of the time series structure. So that's one thing that happens here as well. And again, it's a bit complicated how that happens, but we end up sorting based on the image dates and then using the indices of that sort to sort all the other data like the bands and the tiles and things like this. And then finally, we look to convert these into more standard formats. Lists are a very unusual format to store data at scale in, so we move them to byte strings for more efficient storage and standard loading by data loaders wherever possible. And then we write to Parquet. And that's essentially what this code does. Is I'm just scrolling down to show you what's in here, but just note that it's not necessarily going to be entirely obvious outside of the comments for many of you, and don't feel too intimidated by this. The code has been tested to run. It works really well. It's very robust, and I don't see a lot of problems from this. And just note, it's not really adding anything new to the data. It's simply just reformatting it for modeling later. So essentially, that's the function to do all the work. And then down here we have, you know, we're dealing with loops of data. So we're looping through, in this case, again, the different bounding boxes and years for the training data set. And there's only one bounding box in year for the test data set. So, and then finally, so we go down here, we do eliminate any existing partitions from reprocessing again, in case you were restarting this script because it took too long, and then there's just a for loop to run the code. So again, we're just calling that function with some very simple input and output links, and then a file, so or a partition, I should say. All right, so that's that. Now, after you've run all this, you will have something in your Databricks file store that looks something like, I'll show you the output of the final. It'll be something like this. So we have 7 different bounding boxes. Within each of these bounding boxes, there'll be different years available. In this case, I think I didn't run this all the way through, so you'll see some of these only have 2 years, but we actually have 3 years in the final zip file for all of these because this is the training data set. So as we go through the partitions, we have bounding box year, and then we don't have CDL as a partition in the final one. This is how we did it. This is an earlier one. So you will see at this point, you will actually see the data, not the CDL as a partition. So, but you will have something like that. And again, that's in a format where for part 2, we can show you how to create data loaders that are going to take advantage of the time series format then. So, all right. And then I wanted to show finally what you can do to view this. And again, this leverages some of the strengths of Databricks. It has some very nice abilities to query the data and also plot it with interactive plots right in the GUI itself. So typical imports here at the top. And then again, we'll make this code available to everyone. But to show you what it does, we want to mainly focus right now on the processing after part 2. As I mentioned, part 3 has the exact same data, just in a different format. So we could write a few different functions to do the same thing we're going to do here with the part 2 data. It's just a couple different functions to view the data. So first we read in the data. When you do read in the data, it looks something like this, and I'll run this because it'll keep my cluster alive, and hopefully during this live demo it works. But if I run this, it doesn't take too long usually. You'll see the Spark job run, and the nice part about Spark is that you can kind of see here how long it took me to run each part of my code. So we load the dense test data, and this is the output from part 2. And so now I have this. If I wanted to, I have a function here also to convert to NDVI because it's a nice way to view. So we actually add a column for NDVI. So, but one function you're going to want to know really well is just the display function. So you can display that particular Parquet file that you just loaded. So when I run this, it's actually going to, I'm not going to run it here. It takes like 30 seconds, but what you're going to see as output is a table just like this. And so it'll plot up to a certain number of rows, depends on how many columns you have too. Here it plotted 10,000 rows. But you can kind of scroll across and look at your data, and actually you can sort it by whatever you want to sort it by too. So if I want to sort the column, I can sort it ascending or descending. There's all sorts of things you can do. In this case, I believe it's probably the first 10,000 rows are all from the same date. In this case, so we're not really seeing a difference. You could sort it by CDL. So in this case, we could see, again, we could see the data however we want to see it, I guess. We could sort it by lat long, etc. All right, so as you can see, this, as we saw earlier, the test data set actually has a lot of different crop types in it. So we're going to take this and we're going to view some of these. We're going to pick, these are actually, each of these is a specific date and a specific pixel. But what we want to view is, so this particular pixel, this is the center point of a CDL pixel. I want to see all the data. I want to see all the data from one of these pixels. I don't want to just see one. I don't want to see a table of band values. I want to see a time series of maybe NDVI. So what I do is I use this NDVI function up here, and I have a function down here to display the table of data for one pixel. So I picked out one pixel. In this case, it was one that was cotton. And so what I did was I took the original data frame and I used a dot where, and dot where is essentially a filter. So I'm filtering for primarily this pixel. Now, likely I don't need to add in this case, I wouldn't need to add in these other factors like it's cotton and it's, this year. I put these here just to, for a reminder, but because this is only 1 year and because this pixel is unique, you're going to get the same results if you had just that pixel. And then at the end, I do a dot with column, which essentially adds a column on the end where I can also run a function on each of the rows. And so this function is that NDVI function, and we call this a UDF, a user-defined function in PySpark. And this will create NDVI values. And so that's what we have now. I'm just viewing this single pixel. I have 37 rows. So I had 37 scenes, unique scenes that I sampled from on unique dates for this particular pixel. And you can kind of sort by date here, and then we can see how this looks as we go down here. And at the very end, I have my additional column NDVI that I can view. Now the nice part is I don't have to create a visualization from code. I can actually just add one. And I did that already right here, but I'll show you how that works. Again, just by, if I take this, I can just click on visualization, and I can click on the type of visualization I want to use. So I go to scatter plot. I could choose that I want to actually plot by scene date, and then for the column on the Y, I want NDVI. And here we can see it actually generates that plot for me as a preview. Now it allows something that I want, and I want to color by this scene. I want to actually color it by the scene classification layer, and that's the group by column. So once I do that, I just save this, and it adds that column in, or that visualization in. And it's interactive. Again, you can highlight it and it'll show you the value, the date, stuff like that. You can zoom in if you'd like, or whatever. But it's as easy as that to create plots in Databricks. All right. So this is also allowing us to confirm that our data was processed correctly. So as I look at, you don't know this from this dot here, but if we were to go back to part 2 and we were to look at some of the scene classification values, we'd see that a value of 5 is not vegetated, a value of 4 is vegetated. So if I go here and look at this, well, I see just what I would expect. A value of 4, if I select this off, it'll remove it. But yeah, I see right here around July that we start to see vegetation forming. And for this particular crop, it's actually cotton. That seems about right for that area. And then it's unvegetated outside of that. And there's a few others. These blue ones are actually the cirrus cloud classification. So it's a quick way to verify that everything looks properly processed at the end. We see what we would expect to see with an NDVI curve. The scene classification layer seems to be correct, labeling as vegetation when we see the peak in NDVI. That all makes sense. So let's move down and do that again. I picked out another pixel, in this case a rice one, to confirm that. And this is the visual that I got out of that. So again, a very clean, very nice trend in NDVI over the entire year, and we can see there's probably just a single crop grown in each of these cases. In this case, again, vegetation. The colors are different, but you can see for class 4, it's vegetation. It peaks right here in the middle of the year, middle of the summer, when we would expect the crop to be growing, and it's labeled as rice, and that's what we expect. Now we took there was actually a double crop within the test data, so I wanted to view that as well, see what a pixel of that looks like, and it again, just as we would expect. So earlier in the year, this is going to be the winter wheat crop. And we see that the vegetation peaks, it's labeled as such, and then we see that it must have been harvested, and then there's a very low point where in the NDVI where it's also classified without vegetation, which then peaks again when the soybeans are at full growth. So, and this is labeled as winter wheat and soybean. And then finally, I use a soybean one. Well, actually, I don't think I have a corn one as well. But again, double checking all of these. Again, we're seeing the peak. We're seeing it labeled properly with a few scattered clouds. These are labeled as light clouds or cirrus clouds for each of these. So this is a corn pixel, and this is a soybean pixel. So again, just some different visualizations that are possible. And you can do many other types of visualizations as well to double check the data. But this shows that we have our data formatted in a way that's ready for time series modeling, where we can start doing crop predictions. But the next step will be to get these formatted for a data loader, or to basically pull these into a data loader, and prepare them for modeling. And so that will be part 2 of this series. So this concludes the demo part, though, and yeah. So let me know if you have any questions in the chat, but we appreciate you tuning in. Thank you. Erik?
So for the summary of part 1, we covered how APIs can allow us to automate and scale very large data processing pipelines in preparation for analysis and model building. We covered how storing data in Parquet format and using Spark and Databricks to query and pivot or manipulate the data enables rapid investigation and transformation. The Parquet file format also has useful abstractions like partitions, which are also directories, which help us process the data in a more efficient manner. And a convenient form for modeling time series imagery data involves storing in Parquet table format, with each row representing a pixel for a given time interval and having columns of band values, scene dates, scene classification values over that time interval, and scalars for latitude and longitude representing the center point of the pixel, which could be substituted for any other geo-referencing system like Uber H3 Hex or Google S2 Cells instead, as well as, lastly, but most importantly, the prediction target, which is what the model will use to inform its learning processes. So looking ahead to part 2, we will process the data to prepare for model training using TensorFlow datasets. We'll properly split the data into train val test splits to avoid data leakage. We'll convert the irregularly spaced time series imagery into bucketed time series to prepare for model training, and we'll modify the CDO labels to align with our training goals. Thank you for joining us today.
Erik and John, thank you for the wonderful presentation and demonstration. Before we transition to the Q&A session, I want to remind you there will be one homework assignment which you will be able to access from the training page on March 19th. Answers must be submitted by Google Form with a due date of April 1st. To receive a certificate of completion, you must attend all 3 live webinars, complete the homework assignment by the deadline, and you will receive a certificate via email approximately 2 months after completion of the course. Below is the contact information for Dr. John Just and Erik Sorensen, along with links to the ARSET website and social media. If you enjoyed today's webinar, we hope you will sign up on the ARSET listserv to receive notifications of future trainings, and follow us on Twitter for other relevant announcements pertaining to NASA's Earth Sciences. We will now transition to the question and answer portion of today's training. Please enter your questions in the question and answer box, and we will get to them in the order that they were received. We will post the question and answer document to the training webpage before the start of next week's training. Thank you.
Okay, hello.
Yes, John, we can hear you. Wonderful.
Perfect.
And looks like Natasha's bringing up the Q&A doc. Great. Thank you so much. And for everybody that's been submitting questions, really great questions have come in. So thank you to everybody that has posted them. Again, it's not too late. Please do enter them in the Q&A box and we'll get to them in the limited time that we do have available. So jumping right into it, question 1, is there any statistical analysis between interval grouping and interpolation? I mean, why exactly is interval grouping used in the CDL algorithm?
Okay, so I tackled this one. This is John. The interval grouping we used is just simpler. It's easier. It doesn't require additional assumptions of smoothing that you need for interpolation. And also that's the method used by the CDL. So we just went with it. If you wanted to go forward with some type of interpolation, you could.
Great, thanks, John. Question number 2, for the CDL model, why is the accuracy changing from 85% to 95%?
I can take this one. This is Erik. So yeah, the accuracy of the CDL differs between different crop types. There's many different crop types that CDL makes predictions on, and each of those predictions have varying accuracy. Specifically, generally the more common crops, it has a higher accuracy rate, like corn and soybeans, but it's less accurate on the more uncommon crops like sorghum. There's also there's a link posted here kind of discusses some of the different metrics, including the user versus producer accuracy, which is related to the common labels and how that impacts the accuracy.
Awesome. Thanks, Erik. Question number 3. In machine learning, working with satellite data, which will be the minimum amount of images that you need for the model?
I also answered this one. So I would say that the number of images or the time series that you need varies depending on kind of your use case and the complexity of the task for the model. For our task in this training series of predicting the CDL in real time, we included about 80,000 time series of pixels with an average of approximately 60 pixels per time series for the training set, which seemed to work quite well. And we'll get into some of these details in part 2.
Awesome. Thank you, Erik. Question number 4. Why not use radar, synthetic aperture radar sensors with 12 bands of Sentinel-1A to improve accuracy and overcome the factors that can affect the quality of satellite images?
Yeah, that's a good question. So I answered this, and really you could definitely do that. You could combine SAR with optical, and you could improve your temporal resolution, and you might even be able to, hopefully get more accurate results on your detection of crop types. However, it's more complex, and this is already, as you guys probably have seen, it's some fairly complex code, and we wanted to really try to pick a narrow scope. So we just wanted to use Sentinel-2 for that reason. Also, Sentinel-2 is available free at large scale. So if we tried to use other data sources, it could get very complex, pulling from different sources and then trying to combine them and model them. So we wanted to provide a minimally useful example here.
All right. Thank you, John. Question 5. What would be the Sentinel-2 image quality if we would apply cloud masking between the scene classification layer and the quality assurance 60 bands?
Yeah, I don't expect this to actually change the quality of the detection of clouds a whole lot. Really, I think from what I know about the QA60, it's just the kind of the same version of the SCL, but applied to the level 1C, the top of atmosphere processing. So I wouldn't expect much difference there. Now, if you're using a different cloud detection algorithm like what they have on Sentinel Hub, you might get better results.
All right. Thank you, John. Question 6. What analysis do you use to convert gaps due to scene classification layer errors into appropriate values, such as missing value imputation?
Yeah, that's a great question. I'm kind of looking ahead here to probably have to solve in the next parts. But the strategy that we did is we actually didn't impute any missing values due to things like SEL errors or clouds, but rather we'll pad the missing values in the time series with a constant value. which when we go to part 3 and implementing this in data loader, when we actually train this in with a CNN, the CNN this is kind of basically telling the CNN to impute the values for us implicitly during its training process. So, and again, we'll get into more of these details in the next 2 parts.
Great, thanks, Eric. Question 7, what do we need to create a crop data layer for Morocco, like the one in the US?
Yeah, these are some great questions. And, whether you're talking about Europe or Morocco or wherever you're from, if you want to do this for your area, one way you could do this that we recommend is to simply do what we're doing here, train your model on the US CDL data, but maybe sample the CDL so that it's more, formed around the type of crops you have in your area, whether that's Morocco or Europe. And then so you get this model trained on that type of crop, and then try predicting on your area. So pick out some area AOIs from Morocco or Europe or wherever you're from, and go, run the part 2 Sentinel processing script, get the data, and then run part 3 and manipulate it, and then predict on it, and see how it does. And if it looks like it's reasonable, maybe you're done. If it doesn't, you might just need to fine tune, but you'll need a lot less data to fine tune than you would if you tried to train from scratch for your area.
Great, John. And this one is very much kind of follows on the heels. That last question is, please, how can I download the cropland data layer plots, and what kind of code should I use to have them?
Yeah, and great question. Yeah, so let's see. So the actual plots are, I don't know if this is referring to the plots in Databricks, or if this is referring to the actual data, the CDL data, but we do have, like, within the script, basically the first script, that's where we actually obtain all the CDL data. It only takes about 5 minutes to run. And so if you run that, it's really, you don't have to change anything. It will get all the data for the area of interest we've pre-selected for you. And then, you can start, running the plots. You could take some screenshots of them. You could download them directly from Databricks. But that's, hopefully that answers your question.
Great. And question 9, is hierarchical data format version 5 also a common file format used in remote sensing?
Yep, good question. I'm not sure if it's a necessarily a common file format specifically for remote sensing, but certainly when you're working with large data and distributed cloud computing, HDF5 and Parquet files are very common when working with this type of data. So it can certainly be used for remote sensing data like we do in this training. And yeah, it works very well.
Great, thanks, Eric. And I will say that yes, NASA does distribute a lot of different data products in HDF5, so that is quite common file format for NASA. And question 10, can we use Xarray to make the process easier to handle?
Yeah, I'm sure if you liked other functions in Python besides raster.io, like Xarray, sure, I'm sure that you could probably substitute for that. All I would recommend is, like, just compare it to the original function. So, run the same exact data through the original, make whatever modifications you want with Xarray or whatever functions you like. Run it again, get the data out, and make sure that it matches what the original output.
Great, thanks, John. Question 11, can I run the code on Google Colab?
Yeah, this should be possible as long as you kind of have Spark installed. You can get Spark installed on your Google Colab instance or whatever environment that you're running in. I will note that if you just use these Python files directly in Google Colab, it won't likely work without making some changes. The biggest change is likely the file paths for where you store the data. Most of the files paths that we work with in Databricks uses the Databricks file store, which is not going to be available in Google Colab. So those will need to be changed. But yeah, this code that we generated is generalizable to the computing environment that you're using, as long as you can get Spark installed.
Great, thanks, Eric. And question 12 is very similar to question 7. It's, can I try on other areas of interest that are not within the United States?
Yep, and it's very similar to question 14 as well. I know there's a lot of questions on this. And yes, this is very, very much intended to be applicable to other areas. We really intended for you to try this out on the CDL in the US, get a feel for how it looks, to try and build a model at very large scale on predicting crop type. And then you can apply it to your area. So that, as I mentioned before, that could be just that you pick out crops from the CDL that are simply matching the crop distribution in your area, and then once you have a model trained for those crops, you can apply it to areas that from your country or your region.
Great, thanks, John. And I think just trying to be respectful of everybody's time, maybe we'll end it on this question here. So question 13, do we resample Sentinel-2 data to 30-meter spatial resolution anywhere in the code?
Yeah, that's another good question. If it wasn't clear, we are not like actually resampling. What we are doing is we're just sampling the rasters. So we're trying to move from raster format, a spatial format, into a tabular format because it's easier to work with. So each row of the pixel or each row of the table, finally, the output of part 3 ends up being like a single CDL pixel for a single year. So it's kind of a 30-meter area that represents. And then we have a time series of imagery associated with that we use to train our model on, and then we can same thing for the test data set. So that's what that final table actually represents. So each row is a 30-meter pixel, but we didn't actually like resample anything, so to speak. We really just we're sampling data and putting it into a specific time series format so that we could model it. So we moved from spatial to maybe you would say vector format, so to speak, and we have the ability to move back to spatial later.
Wonderful. Well, we do realize that we're 15 minutes over the time, but thank you so much for everybody that did submit a question. And we know that we did not get through all of them in today's part 1, but what we will do is address and answer the rest of these questions that we did not go through in today's part, and we will post them before next Tuesday, which is the next second part of this webinar series. So we'll have them posted to our training page before next Tuesday. John, Erik, thank you both so much. I mean, you guys knocked it out of the park today. Just tremendous job. As we were wrapping up, I just wanted to give you an opportunity if you wanted to, any closing comments that you might have for the participants today.
Yeah, just thank you everyone for attending. We really enjoy seeing everyone from all over the world kind of commenting in the chat, and we love to answer your questions, see that you're learning and have some use cases for this. We really tried to make this scalable in general for you all. So reach out if you got any questions. Our emails are in the documents, and we look forward to the next couple training sessions as well, where we show you how to model with this data.
And Erik, did you have any closing comments for
yeah, ditto. I'm just ditto John's comments. We're excited to kind of see what the participants do with this training series and some of the results that they come up with. So yeah, definitely send us any examples of the things that you're able to do with this pipeline. We're excited to kind of see some of the results. So yeah, thank you all.
Great. Well, John and Erik, thank you both again. And I also want to acknowledge the ARSET team that is working in the background. You might not have heard their voices. You might not have seen them, but that is Natasha Johnson-Griffin, Selwyn Hudson-Odoy, and Sarah Cutshall. So thank you to the ARSET team. And again, I want to thank all the participants. We know that you have busy schedules in your personal life and professional life. So we really hope that you got a lot out of this training. And we do hope that you'll join us all at the same time next Tuesday for part 2 of the webinar series. So thank you all again, and we look forward to seeing you next week. Thank you.
Thanks all. Bye-bye.
Thanks.